Today we are going to talk about double chain silicates. Well, not truly about double chain silicates, but the most important group of minerals amongst double chain silicates, that is the amphiboles. There are two major group of minerals in chain silicates. The single chain silicate are called as pyroxenes and the double chain silicates are called as amphiboles. Since both have similar kind of structure, so there are a lot of similarities in the two group of minerals, and there are some dissimilarities which distinguish their structure and to an extent their composition. But first let us look at what is the general formula of amphiboles, and it can be written as now. As you see, I have maintained some distinctions or distances between these letters. Now we will fill the spaces in between. This is 0 to 1, this is 2, this is 5 and this is 8. Now these letters represent different sets of cations. If we start with the lowest coordination number, then this represents dominantly silicon and with silicon aluminium. As we can see, on the other hand, for W we have written 0 to 1, which means that this site can sometimes be vacant also, or at the most for this formula unit one cation can occupy this site, and it represents, as this represents the smallest coordination, this represents the largest coordination, and therefore the cations which are present here are commonly sodium and potassium. In this site we commonly have again sodium and calcium. Besides, iron and magnesium can also be present here. In the Y site, which is an octahedrally coordinated site, we can have iron, magnesium, manganese, aluminium, titanium and chromium. As you can see that the structure of amphibole is such that it can have a wide ranging chemistry. For example, you can have an amphibole without any W cation, which means a vacancy here. Similarly, you can also have an amphibole which has not got any calcium or sodium, only aluminium, only iron, magnesium. So therefore, this gives rise to a wide range of amphiboles. So let us look at, in light of this general formula, some of the amphibole compositions. We will also see later that it is not only the chemistry which is highly variable, but also the structure. So let us look at some of the common amphibole names. So one of the first amphibole I would like to mention is anthophyllite. Now you see, in terms of this, we can write its composition as FeMg 7, Si8, O22, OH whole twice as a general formula. You see that it has vacancy in this site, and these two sites are combined together to produce 7 cations, and this represents one type of amphibole which lacks calcium and which lacks higher cation coordination. The other common amphibole is coming tonight Grunerite series. And you see, we will derive the formula from this. The Cummingtonite formula can be written as Fe2Mg5Si8O22OH whole twice. And the Grunerite is the iron end member of this, where this entire thing is iron. It becomes Fe7Si8O22OH whole twice. Then we come to the next group of amphiboles or next series of amphiboles, which is actinolite, tremolite. Now in this we were lacking up to this calcium. In the X position, X cation position, we have calcium here. For actinolite we have iron, and for tremolite we have magnesium. Other than these, there is one more group of common amphiboles which are very important petrologically or geologically, that is represented by the from tremolite, which I will again write the formula. One can form hornblende. By substituting sodium in the vacancy, substituting some sodium in the X site, so it becomes NaCa, substituting some iron in this site, and substituting some aluminium in the tetrahedral site. These substitutions take effect with increasing temperature. So, therefore, tremolite with increasing temperature transforms to an amphibole which is commonly present and is known as hornblende. The other group of amphiboles which is commonly present and significant is represented by sodium potassium amphiboles, and one of the most important member of this is glaucophene. This can be represented by a formula like Na2Mg3Al2Si8O22. Now, as you can see that in this a larger cation is present instead of in this position. The Y position is substitution of aluminium for iron, magnesium or iron, and we have silicon and oxygen in the normal proportion. Now, this amphibole is commonly present in ultra high pressure rocks. Besides these common amphiboles, there are range of other amphiboles. For example, in sodium potassium amphiboles with slight variation in composition, the Rebeccaite, another potassium bearing amphiboles can be present, and similarly there are a range of amphiboles. The composition of amphibole is so complex that its classification has been a subject of several studies, and the classification of amphibole requires a significant amount of mineralogical and chemical data, and the last classification which is normally followed is after Leakey et al. So, after knowing the types of amphiboles, we will now start considering or looking at its structure. As I mentioned that the structure of amphibole is similar in terms of basic chain silicates. The difference is that it has double chain silicates or two chain silicates. The B axis, as in amphibole, is of the similar dimension, that is of 5.2 angstrom. The A axis is half of what in pyroxene is half of what is there in amphiboles. So, there are structural differences between the two. The other major difference between amphibole and pyroxene is the presence of volatiles either as OH or with fluorine and chlorine. So, there are compositional and structural differences. Now, this leads to the differences in physical properties of the mineral or crystallographic properties of the mineral as well. The cleavage angle, which is described by I-beam structure in pyroxene, describes a cleavage which is at 8793 degree. In amphibole, because of the distortion introduced by the variable chemistry and the presence of the hydroxyl ion, this angle assumes the cleavage angle assumes 56,124 degree. So, therefore, this becomes a very distinctive property of amphiboles in hand specimen as well as under microscopes. So, the properties of amphiboles are controlled by their chemistry. That is, the different kind of amphiboles when we are looking, they describe different types of amphiboles. Similar to pyroxenes, the amphiboles also crystallize in two different crystal systems, that is the orthorhombic and monoclinic. The orthorhombic amphiboles were the ones which we first described, that is anthophyllite represents a orthorhombic amphibole. Some of the amphiboles with similar composition can either be in the crystallized in monoclinic system or in orthorhombic system. So, it depends upon the condition under which they are forming. If we look at the way from melt crystallization takes place, the pyroxene crystallize earlier and amphiboles subsequently follow. But in that sequence, if the composition is right, first the orthorhombic amphiboles crystallize followed by the monoclinic amphiboles. So, this tells us that the orthorhombic amphiboles relatively have higher stability or are stable at higher temperature. Now, in the two chains, the opposite apices of the tetrahedra, they describe the M sites, M1, M2 and M3 sites, and the bases describe the M4 site. So, there are 4 M sites which are occupied by different cations. Now, they are not of fixed coordination. If the cations are larger, they can be 8-fold, and if the cations are smaller, they can be 6-fold. The double chain silicate structure is well explained in figure 1, in which you can see that the repeat C distance is 5.2 angstrom. Because of this complexity of the structure of the amphiboles, we can sort of summarize the types of amphiboles and describe their conditions. For example, when we talk about Ca rich amphiboles, so the Ca rich amphiboles are of high symmetry and they occur at wide temperature range and pressure. Of Ca poor amphiboles, they are of lower symmetry and their chains collapse on cooling. Then there are Ca free amphiboles like anthophyllite. They are normally orthorhombic structure and their lower temperature values, the chains vary in size. And then we have proto-amphiboles which are high temperature amphiboles, and they occur as pure Mg end members at very high temperatures. So, these are the sort of summary of the types of amphiboles. However, there are bigger complexities, that is the substitutions which I described in case of like in hornblende. This substitution is known as the Pargasite. There is a substitution which is known as Charmak molecule substitution. There is a substitution which is simple FeMg exchange substitution, and there is a combined Pargasite exchange which involves sodium as well as the Charmak substitution combined together. Now, these substitutions are not 100%, means that when we try to look at the amphibole compositions, we find that there are gaps in solution, and these gaps in solutions are well reflected in the diagram which you can see. This diagram is a quadrilateral diagram in which the upper part is iron end member, the left is the magnesium end member marked by anthophyllite, and the extreme right part is the Fe end member. So, as you can see that there is anthophyllite which is at the extreme left end, which means that it has some amount of iron and it has some amount of calcium. The calcium is at the top. Then there is a gap in solution, and the sequence of Cummingtonite grunerite amphibole commences. So, there is a solidus or there is a subsolidus gap between anthophyllite and Cummingtonite grunerite. That at the higher calcium end member is represented by actinolite. In actinolite, there appears to be a complete solid solution between the iron and the magnesium end members. So, this diagram actually shows the possibilities of various type of amphiboles, dominantly the calcic and subcalcic amphiboles being present. When we try to observe the 4 M sites and the cations which they occupy, then that is illustrated in the accompanying table. Now, in this table you see that the M4 site can have iron, magnesium, calcium. The magnesium end member, where in M4 site magnesium is there, and M1, M2, M3 site is also magnesium, is anthophyllite, where in M4 site iron is there, and in the M1, M2, M3 sites magnesium is there, that is Cummingtonite. In both of these, the A site is vacant. Then in grunerite, both the M4 and M1, M2, M3 sites are occupied by iron. In tremolite, the M4 site is occupied by calcium and the M1, M2, M3 sites are occupied by magnesium, and as the A site is vacant. And in ferroactinolite, the M4 site is occupied by calcium and M1, M2, M3 sites are occupied by iron. In case of hornblende, the M4 site is occupied by some amount of sodium besides calcium. The A is more or less vacant, and in M1, M2, M3 sites there are significant substitutions of Mg, Fe, Mn, Al, ferric iron, titanium and aluminium. In case of glaucophane, which is present at in very high pressure rocks, the M4 site is occupied by sodium and the M1, M2, M3 sites are occupied by ferrous and ferric irons both. In Rebeccaite, the M4 site is again occupied by sodium and the M1, M2, M3 sites are occupied by ferrous and ferric iron. In Arfvedsonite, which is a sodium amphibole, the A site also has significant amount of sodium, and there are some lithium amphiboles are also present, in which case the lithium occupies the A site. So, we see that there is significant amount of variation in the amphibole composition as well as amphibole structure. Now, this allows the amphibole to be present in wide range of geological setting, which includes from magmatic rocks to large range of metamorphic rocks, as well as it is present as a detrital mineral in sedimentary rocks. The classification of the amphibole, as I mentioned earlier, is a complex thing and it requires complete chemical and sometimes crystallographic information, and that is explained in a diagram which is seen here. In this diagram, you see a generalized classification of amphiboles, which is a 3-axis classification. Now, in these 3 axes, one axis is aluminium, the other axis is sodium, and the third axis is sodium potassium. And you see that there are many variants of amphiboles are present. For example, along vertical axis in this, the lowermost part is calcic amphibole, the intermediate part is sodic calcic amphibole, and the upper part is sodic amphiboles. In the horizontal axis, you have tremolite, magnetiotremolite, and actinolite, and Schermerkite present, and Schermerkite is present. Okay, so this classification again signify the wide range of amphibole compositions which is present in nature. In hand specimen, normally amphibole occurs either at stout prisms or in bladed forms, and it is easy to identify. Under optical microscope, the amphiboles are easy to distinguish because of their characteristic cleavage and pleochroic colors. The calcic amphiboles are pleochroic in shades of green. The sodic amphiboles are often pleochroic in shades of blue, and their pleochroism combined with cleavage helps them to distinguish from pyroxenes. The amphiboles are useful petrogenetic indicators both in metamorphic as well as in magmatic rocks. In fact, in metamorphic rocks, a amphibolite facies, which is the largest, widest range of rock, is named after them. Hope you have enjoyed learning about amphiboles.